A function can have an absolute maximum or minimum and a local or relative maximum or minimum over a given domain. And we'll go through these different cases. So an absolute maximum at some number value c occurs if the function at c is the greatest value of the function for that domain that's been given. So then this would be called the maximum. And then the opposite is true too. It would be a minimum if the function at that point c is less than all of the other x's in that given domain. So that's if it is the absolute maximum or minimum. We can also have a local maximum or minimum in a given domain where we just see the graph go up and turn around at a given point. So let's look at a specific example to help us see what's happening here. So here are three functions, and we're just going to sketch them out quickly so we can talk about them. So the function x squared has an absolute minimum at the point x equals 0. And that's the lowest point. And if we were to be given the whole domain or a restricted domain, x equals 0 is the minimum of that function. If f at x equals x cubed, we see this function. And this function doesn't have a absolute maximum or minimum. So it does not exist. There's no max and min. Does not exist. There's no absolute maximum or absolute minimum or local max or local min because it continues on through the whole. It goes to infinity. Okay, let's look at this one. So first, let's figure out the roots of this function. We're going to factor this so we can look at it. Okay. So I know that I have a root at 0. And then I have these other two roots. So this is a perfect square. So if I'm going to factor this, factoring a difference of squares, then I would have x minus root 5 and x plus root 5. So then I have root 5 here and root 5 here. So I know that the function passes through those points. I also know that I'm going to be starting in this quadrant and ending in this quadrant. That's just the rules that we covered in functions. So I know I'm going to be doing this type of motion. What I don't know is this value and this value. I don't know the maximum and the minimum. So what I need to do here is I'm going to take the derivative of this function, 3x squared minus 5, and set this equal to 0. 3x squared minus 5. So x is plus or minus the root of 5 over 3. And this is going to be my max and my min. 5 over 3. Okay, so from these examples, we can see that a function may or may not have a maximum or minimum value. However, if a function is defined on a closed interval, so let's say we were to say, okay, just in between these points here, then we must have both a maximum and a minimum value. So how do we find these maximum and minimum points? So these points occur when the derivative, so the max and min occur when the derivative is 0. Okay, so if f has a local maximum or minimum at some given value c, then either, so these are the two cases, the derivative of the function is 0 or the derivative of the function does not exist. And so just as a quick counterexample, we want to remember that this doesn't always hold true. So if we were to take the derivative of this function, we would have 3x squared. And this might say, oh, look, this happens when x equals 0. But here we don't have a maximum or minimum. This is just our same graph as before. And we already know that this is not a maximum or a minimum. It might be a critical number because it might be telling us that something's happening in the graph, but it's not actually a maximum or minimum value. Okay, so the idea behind Fermat's theorem is that when we are looking for maximum and minimum values, these could also be called extreme values, we're best to start at the values of c where we know that c equals 0 or the function doesn't exist. So these are just the critical values. So we're going to look at some examples. So the first step I'm going to do is to take the derivative. Okay, and now I'm going to factor this. I'm going to set it equal to 0, and I'm going to factor it because I want to find when this can equal 0. And now I'm going to take a trinomial factor, and I'm going to find out that the critical values, so my critical numbers here, occur when x is -4 and when x is 2. So those are my critical numbers. So then I would plug these values back into my original function to see whether or not they were maximums or minimums or maybe nothing at all. So here's another example where we've got another function, and this function could actually be represented as a piecewise function. Remember from last year. So we have the situation where the function is actually just x, and this happens if the value of x is bigger than 0, and the function can also be negative x if the function is less than 0. And if we take the derivative of this, we actually can see that the rate of change, or the slope, is 1 if x is bigger than 0, and -1 if x is less than 0. So the function at 0 does not exist. So here's a case where we can't get 0 here. We can't get a slope of that point. So here's my graph. Here's my function. We don't know, like we can't find a tangent here. We don't know what the tangent could be. This does not exist. So this is where we would see this point, g at 0, is a critical number. Okay, so let's say we have we want to find the absolute maximum values on a continuous function in a given interval. And the interval is from a to b. So we're going to first find the values, or find the values of f at the critical numbers in that interval. So we want to find the critical numbers. Then we want to find the values of f at the endpoints. And then we're going to figure out what's what. Let's try an example. All right, find the maximum minimum values of the function over this interval. So step 1, let's find the critical numbers. 3x squared minus 12x plus 9. Factor, set it to 0 and factor. Trinomial factor. Okay, there are my critical numbers. And now I'm going to find the value of that function, the parent function, the original function, at all of these different possibilities. So the lowest x input is -1. And then I have this critical number of 1, another critical number of 3, and then the maximum in the interval is 5. And so I would just calculate this. I put this all in. If I put -1 into this expression here, I'm going to end up with -20. If I put 1 into this expression here, I end up with 0. And if I put 3 in here, I end up with -4. And if I put 5 into there, I end up with 16. Now I'm just going to look for my maximum. There's my maximum right there. And my minimum. And there's my minimum right there. Okay, for practice, page 176, numbers 1, 3, and 4.